Hello, we are back again with another lesson for Engineering Calculus 2. I'm still your lecturer, and our outcomes for this lesson is number 1, solve the particular antiderivative satisfying the equation and initial condition. So we will be learning about um, basics of differential equations. So since we have a differential equation, we need to know how to get the antiderivative, which we have learned from our previous lessons, and also to solve the complete and particular solutions of differential equations. So these are our objectives for today's lecture. So here is the outline of the lecture. So we will start with definition of differential equations, some terms. We will not really dig deep to differential equations because that is a different subject. So we will just touch up the basics, and we will learn what is what do we call the complete solution, as well as the particular solution with initial conditions. And then we will also do some practice problems with application, particularly in rectilinear motion. So let's start. So differential equations, so from here on, let's just call them as DE. So it is an equation containing a function and its derivatives, or just the derivatives. So an example, simple example would be dy over dx equals 2x. So we have a function, we have the derivatives. So that is a simple DE. Another example would be dy over dx equals 2x squared over 3y cubed. So we have functions and their derivatives. Another one would be the second derivative of y with respect to x equals 4x plus 3. Okay, so we will not be just seeing dy over dx here. We can also see second derivatives. Okay, so the order, please take note of the terms that are in boldface and italics. So here, the order of a differential equation is the order of the derivative of highest order. So that's quite confusing, but you will see, appears in the equation. So from our first 3 examples, let's define them. So this is defined as a first order differential equation, since the highest derivative you can see is the first derivative, just dy over dx. This as well is a dE of first order, and you guess it right, the third one would be a second order dE, since you have the second derivative here. So the order is just of a dE is just the highest order, the derivative that occurs in the equation. So a function f which is defined by y is equal to f of x, so function of x, is a solution of a differential equation if y and its derivatives satisfy the equation. So what we'll be looking for here are solutions to the DE. Okay. So we have the derivatives. So to satisfy the equation of y and its derivatives, we need to get the antiderivatives. So that would be our solution to the differential equation. So here we have again a simple differential equation. So dy over dx would just be equal to f of x. So what we need to do is transpose dx on the right side along with a function in terms of x, so that we can get the antiderivative of that. We can get the antiderivative of both sides. So we can see the ease of this form. Dy over dx equals a function. So most of the time, what should we do is just get the dx on the right side and then carry out the anti-differentiation to remove this derivative and find the solution of the DE. Okay, so that is not the only form the DE can look like. So as you can see from our example 2, so another form is dy over dx equals g, function of x, all over h, the function of y. So this one, you need to put to transpose dx on the right side as well as h of y to the left side. So now all the variables in both sides are for the left, all are in terms of y, and to the right, all are in terms of x. So the variables are separated and we say that these are separable differential equations. Okay, I hope at this until this you can still follow. Alright, so we have the earlier illustration. Dy is equal to function of x dx. Here we put y is equal to g of x, another function. So the function f is equal to the antiderivative of f of x dx. Okay, so since we put y as gx, we get the antiderivative of dy, that would be gx, and f of x is equal to the antiderivative of fx dx. So we have the equation or the solution to our DE as g of x is equal to f of x. Of course, we have the arbitrary constant c. So let's check. So the derivative of g of x is just equal to the derivative of f of x plus c, which is just equal to f of x dx. So d g of x, that is dy. So we just go back to the original DE. So the complete solution or general solution is y equals f of x plus c for this one. So our y or g of x is just equal to f of x plus c. So I think this equation would be familiar to every one of us. So this equation represents a one parameter family of functions depending on the arbitrary constant c. So the graphs of these functions, which we will be seeing in the next illustration, form a one parameter family of curves in the plane. So just one curve of the family passes through any particular point. That's any point x comma y. So let's have an illustration to better understand this explanation about this one parameter family of function and one parameter family of curves. So let's take the first example, dy dx is equal to 2x. Then transpose dx to the right side. We have the differential equation dy equals 2x dx. So to get the antiderivatives, we have the integral dy is equal to the integral of 2x dx. So that would be equal to y plus an arbitrary constant c sub 1 equals, this would be 2x squared divided by 2. So that would just be x squared plus the arbitrary constant c sub 2. So since these are arbitrary constants, we can combine them. Let's put c1 to the other side. That would be c2 minus c1. Or since they are arbitrary, let's just call it c. Okay, so this is our complete solution for this differential equation. Y is equal to x squared plus c. So if, as you can see, this just looks like the equation of a parabola, which is y equals x squared plus c. So our complete solution represents the one parameter family of functions. So let's try to plot this equation, y equals x squared plus c, for different values of c, and we will get this. So these are the graphs. So we have y is equal to x squared plus c. This blue one would be where c is equal to 1. Okay, this is the origin. This is 1. The red one would be c. This is y equals x squared plus c, which is equal to 2. Okay, so as you can see, this is the family of functions, and this is the family of curves. You can see the curves are just moving the vertex along the vertical axis or the y-axis. So this is our family of curves, and if you can recall earlier, we mentioned that each a particular point will be just one of these curves will just pass through that particular point. Let's say 2 comma 6. Okay, x comma y, which is 2 comma 6. This curve includes that point and none other else in the family of curves, right? So you have 1 comma negative 1. This would be in this curve, okay, which is where the c is equal to negative 1. So this, the lowermost curve, is c equals negative 4. So you can use any value of c up to, say, from 0 to 100 or whatsoever. But then again, if you plot them, they will just look like this. They will just move the vertex along the vertical axis, and a particular point will just be included, or one one of the in the family of curves will just pass through that particular point. So let's try to find the complete solution for our other examples. So this is the second example. So we mentioned earlier that this one is a separable DE. So we write it as such, where we put 3y on the left and dx on the right, and then we carry out the operation, the integral, the anti-differentiation, to find the complete solution. So as you can observe, we can find the complete solution here by simply using the power equation, or sorry, the power formula. Okay, so this is just y cubed plus 1, so that's y to the fourth, 3/4 of that, 3/4 y to the fourth, plus of course the arbitrary constant c1, and to the right side we have x squared plus 1, that's x cubed, divided by 3, plus the arbitrary constant, that would be c2. So again, these are arbitrary constants, so we can combine them and assign an arbitrary constant c. Okay, so removing the fractions from both sides, so we just need to multiply it by 12. Okay, so 12 multiplied by this side and 12 multiplied by the other side. So 12 divided by 4, that would be 3, that's 9y to the fourth power, that would be equal to 12 times 2, that's 24 over 3, that's 8x cubed, plus 12c, or since it's again it's arbitrary, so we just write c. So now let's we know how to find the complete solution. Now let's learn how to find the particular solution of a first order DE with given initial conditions. So we have the complete solution from, for example, 1, which is y is equal to x squared plus c. So this is our complete solution. If we are going to assign initial conditions here, we have, these are given, okay, y equals 6 when x equals 2. So we are trying to find the particular solution by defining the value of our arbitrary constant. Okay, so for the particular solution, this would no longer be plus c. We will be looking for a value based on our given initial conditions here. Okay, so what we will do next is just to plug this given initial conditions to our complete solution or general solution to solve for the arbitrary constant c. So solving for c, we can rewrite this equation as y minus x squared, and plugging in the values, we have c is equal to 6 minus 2 squared, or simply 6 minus 4. So c is equal to 2. So our equation or our particular solution for this given initial conditions would be, just replace c here with what we have solved, which is 2. So this is now our particular solution with this given initial conditions. If you give another set of initial conditions, of course we will get a different value for our arbitrary constant, as we have seen from the um, example earlier, the sketch of the graphs. We have one parameter family of functions as well as one parameter family of curves. We will try to find the complete solution of our previous example, which is a second order dE. The second derivative of y with respect to x equals 4x plus 3. So this equation can be also written, that equation is just the derivative with respect to x of dy, the derivative of y with respect to x, that's equal to 4x plus 3. So what we need to do here is to, yep, you guessed it right, you need to perform anti-differentiation twice. One for to remove this d over dx, and the second one is for this. So for here, let's write, let dy over dx be written as y prime. Okay, so we will write it as the derivative of y prime with respect to x equals 4x plus 3. So now we will, since you have a variable x here, we can separate the differential equation and put dx on the other side, which will be, so we have dy prime is equal to 4x plus 3 dx. So we will do the first differentiation. We will anti-differentiation. So the integral of dy prime should be equal to the integral of 4x plus 3 dx. So for the integral of dy prime, they will just remove the differential operation and it will be equal to y prime. So y prime or dy over dx. Okay, so that would be equal to, so applying all the theorems and the way of solving techniques in anti-differentiation that we studied earlier. So we'll separate this. This will be the integral of 4x dx plus the integral 3 dx. So we can just use simple power formula for this one. Alright, so for y prime, since we have an integral sign here, we should also have here an arbitrary constant. So let's write that down as C1. So for this, we have, this would be x squared over 2. So we will have 2x squared plus, this would be 3x. So I hope at this point you can follow, and we don't have to discuss in detail how those transformations, how those how the power formula is utilized in this one. And of course, we have our constant of integration. Let's call that C sub 2. So now we have this equation, we have constants C1 and C2. Let's write that down. We transpose C1 to the other side, and let's write that down as an arbitrary constant. So I will write it down as y prime would just be equal to 2x squared plus 3x plus c. Since we are going to do differentiation twice, let's name this arbitrary constant as c1, because in the next anti-differentiation we'll also generate another arbitrary constant which we will call c2. So later on you will understand why we can't combine these constants like what we are doing previously. Okay, so let's have another. Okay, so now we have y prime, or let's write it as dy over dx equals 2x squared plus 3x plus c sub 1. Okay, so now for the second anti-differentiation, we need again to separate this differential equation into dy is equal to 2x squared plus 3x plus c1 dx. So if you can notice, since we will be going to integrate later these three expressions, c1, this constant, will have its own x. That's why we can't just call it as c, because we will be generating another arbitrary constant due to this second anti-differentiation. So let me just write the integral sign here so that I don't have to write it everything all over again. Okay, so in order to find the complete solution for this DE, we need to do the second anti-differentiation. So here we will have the integral dy is just equal to y. That would be equal to the integral 2x squared dx plus 3x dx plus the integral of c sub 1 dx. Okay, so remember here, when you integrate dy, you also have a constant here, but I don't want to call it c1 since we are using c1 here, and the arbitrary constant that will be generated by this anti-differentiation will be, let's call it c2. So right now the constant is here, but let's not write it down for now. Okay, so we have y is equal to, this is another power formula, that would be 2/3 of x cubed plus, this would be 3/2 of x squared plus, this is an arbitrary constant, we take it outside the integral and we integrate dx. That would give us x, so that would be c1 x. So you can see our arbitrary constant from our first anti-differentiation become a coefficient in this second anti-differentiation, and as we have mentioned earlier, we will call the arbitrary constant from the generated from here and the anti-differentiation of these three as c sub 2. So now we have two arbitrary constants, and this is your complete solution for that particular DE. Now we will find the particular solution of a DE with initial condition. So let's use the same example, but for now we have an initial condition where y is given as equal to 2, y prime is equal to negative 3 when the value of x is negative 1. So now we will just plug this in on our previous equations, the result of our first and second anti-differentiation. So we have y, we have the value of y prime and x. So here we can solve for let me write that again. So here we have y is equal to y is equal to 2, y prime is equal to negative 3 when x is equal to 1. Let me check that. Okay, 2, negative 3, and 1. Okay, so we have our very first equation, y prime is equal to 2x squared plus 3x plus c1. So here we can find the value for c1 by plugging in our values in the equation. So that's negative 3 equals 2 1 squared plus 3 times 1 plus c sub 1 or c1. So here we transpose everything to the left, and we have the value for c1 as this would be 2 plus 3, so that would be 5 transpose to the other side, that would be negative 5, that would be c1 equals negative 8. So for the first anti-differentiation, we can write it down as dy dx is equal to 2x squared plus 3x plus c1, which is now we know as negative 8. So for our second equation, we have c1 arbitrary constant, c sub 1 as negative 8, and we have our the equation resulting from the second anti-differentiation, and given the initial conditions, we can plug in those in this second equation. Now we have a value for c1, so that would be negative 8x plus arbitrary constant c sub 2. So now we can solve for c sub 2, plugging in our initial conditions. So we say that the value for y is equal to 2, and x will remain as 1. So we solve the equation. We have here minus 8 times 1 plus, so solving for C sub 2, let's take everything here to the other side. So we have C2 is equal to 2 plus, that's 8, minus this 1 cube is 1, so minus 2 third, and minus 3 halves. So the least common denominator for this would be 6. So we have 6 divided by 1 times 2, that would be 12 plus 48 plus 6 divided by 3. Sorry, this is minus minus 4 and minus 9. Okay, so our C2 would be, that would be 50 minus 13. Oh, sorry, that would be 60 minus 13, or 47 over 6. Okay, so writing down our particular solution for this DE given the initial conditions we have. So the value of C2 is 47 over 6. So we have here y equals 2/3 x cubed plus 3/2 x squared minus 8x, and the plus 47 over 6. So this is our particular solution for that differential equation given our initial conditions. So now that we have learned, we have defined what is a complete solution, what is or a general solution, and what is a particular solution given initial conditions, as well as we learn how to calculate them. Let's extend our knowledge into applications. So particularly in solving word problems regarding rectilinear motion. If you can recall from our first meeting, we already have a short discussion about the relationships of position, velocity, and acceleration. So you defined velocity as the change in position or the change in distance with respect to the change in time. So we write that as a differential equation where v of t, of course, velocity is a function of time, is equal to ds, this would be our position, over dt. We also defined acceleration as the derivative of the velocity or the change in velocity with the change over the change in time. You also have an idea from that first meeting that in order to get the position of an object and given the differential equation for the acceleration or the function for the acceleration, you just need to get the antiderivative twice. Okay, so we get the antiderivative of this and the antiderivative of this to arrive to the equation of S. So mostly that is what we are going to do in solving this rectilinear motion problems. But of course, you already learned how to solve differential equations, do anti-differentiation techniques. But in this part, in applications, we need also to somehow analyze and visualize by drawing the diagrams. So we will be using necessary analogies. So let's take an example. So here we have a particle, and it is said to be moving on a line with a velocity. The unit is given as centimeters per second, and it is a function of time, t, in seconds, none other, and is given by, so we have a note here. Please note that in this equation, so the equation is given by the velocity is equal to 10 times the cosine of twice pi multiplied by the time. And here, the note is this angle 2 pi t is in radians. Okay, so when you're using your calculators, please shift the angle unit into radians. Or if not, you can, if you like to operate on degrees, just convert the radians into degrees. Okay, we will try to incorporate that later in the calculation. Okay, so here it is said the particle is 5 centimeters to the right of the origin at the start of the motion. So find its position when t is, we have 4 required here. T at 0.3 seconds, at 1.4 seconds, at 2.9 seconds, and 3.6 seconds. So to better visualize, we need a diagram for this problem. So here we have a particle. It's moving on a line with a velocity given by this equation, and this is the direction of the motion of our particle. Let's say this is the origin and this is the positive x-axis, and the particle is said to be 1, 2, 3, 4, 5 centimeters to the right of the origin at the start of the motion, that is at time equals 0. Okay, I hope you can follow. For this one, it's really hard to simulate this motion, but we will learn later that this motion is not really just going forward. We'll see when we plug in the values for t on our equation and we calculate the position where the particle is at this timestamps. Okay, so as you notice, we are given an initial condition, which is the position is 5 centimeters and the time is 0 seconds. So maybe now you have a hint that this problem will be involving a particular solution of a differential equation. So now let's try to solve this differential equation. So first, in order for us to easier approach this problem, let's write down our our givens. What are the data available? What are the variables that we can readily use? So we are given an equation for the velocity. So it is 10 cosine. So again, remember that this angle is given in radians, and we are also given initial conditions, which is the initial position is 5 cm 5 centimeters from the origin, and the initial time is 0 seconds. So please be very careful, don't forget to write your units, okay, so you won't be confused later. Okay, so what else? Okay, so far these are the data available to us. Now let's see what is asked in the problem. So what is required to be calculated? So it's already enumerated to us that we are looking for the position, or S, at particular timestamps. The first one of which is 0.3 seconds. So what is S in that? So for B, we are also looking for S at 1.4 seconds. For C, we are looking at, let me check that. That's 2.9 seconds. So basically, we are looking for position. Okay, so given the initial position that we are in 5 centimeters at 0 seconds in the beginning of the motion, so as let's say we froze the time and then we unfreeze it, so time is running 0.3 seconds. Okay, what is the position of our particle? Again, 1.4 seconds, what is our position? 2.9, what is our position? 3.6, what is our position? So how will we approach this problem? Let's write our solution. So we mentioned earlier that we want to find the S at each of these timestamps, and we are given only the function of the velocity as a function of time. But we know also that the velocity is also equal to ds over dt. So now we have two equations both equal to v. It's only practical to equate those two equations. So ds over dt is just equal to 10 the cosine of 2 pi t. Remember, it's in radians. Okay, so now we have our differential equation. So in order to solve this differential equation, we just need to separate the ds and dt by putting dt on the right side, where we can get the antiderivative in terms of t, since t is in this side. Okay, so again, we defined in our required that we are looking for s. Now we have here ds. So if we get the antiderivative of this, we will be arriving in an equation solving for s. Alright, so now let's carry out the operation. I will just write the integral sign here so I won't have to write everything all over again. So now we need to the antiderivative of ds will just be equal to s, and that would be equal to the antiderivative of 10 cosine 2 pi t dt. So this one, applying what we learned from our previous lessons, since you see the cosine in there, we want this to look like cosine u du equals, that would be equal to sine u plus c. So we will make this equation look like this so that we can write it as sine u plus c. Let's do u substitution. It's only practical to let u as our angle here, which is 2 pi t, and the derivative of that will of course be 2 pi the derivative of t. Okay, so we need this equation to look like cosine u du. So cosine 2 pi t, I'll write it in red. So we want it to look like the integral cosine 2 pi t cosine u multiplied by du. So du is 2 pi dt. So from the original equation, we need to introduce 2 pi, and we can only do that by multiplying this equation by 2 pi over 2 pi, or just equal to 1. So applying our theorems, so this constant 10 will be taken out of the integral symbol. So here we have 10, and we have 1 over 2 pi to justify why we put 2 pi in here. Okay, I hope at this point you want follow. We have done a lot of exercises and problems regarding u substitution before. This is very, I believe at this point this is very simple for you. So this would be 10 over 2, that would be 5. So let's write our answer here. So that would be 5 over pi, and since we accomplished this to be cosine u du, we can just simply write sine of u. So sine 2 pi t plus our constant of integration. So remember here, when we took the antiderivative of ds, we also have a arbitrary constant here. We just combine it with the arbitrary constant here, and we call it as just c, the arbitrary constant. Again, we are given initial conditions, so we are looking for the particular solution here. So let's this one here would be our complete or general solution, but what we need is the particular solution, and we can do that by plugging in our initial conditions, these two here. Okay, so writing down our equation in terms of the initial conditions, we have S sub O would be equal to 5 over pi sine 2 pi of initial time T sub O plus C. So we have here 5 centimeters equals 5 over pi times sine 2 pi times t, which is 0. So this would be sine 0. So without getting your calculators, you can imagine that the length opposite of the angle 0 would just be 0. So, or if you want, you can use your calculator to prove that sine 0 would just be 0 multiplied by 5. So that would be 0 plus c, or our arbitrary constant would just be equal to 5 centimeters. So what does that tell us? So it tells us that the particular solution, or the antiderivative of our differential equation, the position s would just be equal to the function 5 over pi sine of 2 pi times the time, still a function of time, plus c, where which is the initial position. Okay, so I hope you recall, I mentioned, I believe in our first lecture, that sometimes, or rather most of the time, the arbitrary constant is just the initial condition. So in this case, we can write down our equation as S equals 5 pi sine of 2 pi times the time plus 5 centimeters. So this is the unit of the position. So whatever we calculate here, we just add the initial position 5 centimeters to it. Okay, so I hope you can still follow. So what are we looking for really? We are looking for the position S at this timestamps 0.3, 1.1, 2.9, 3.6, and we will just be substituting this timestamps to our T here. So at this point, since it is noted that we are in radians, I hope that you will put your calculators where the angle units would be in radians, so that you won't get the wrong answer. You will get an answer definitely, but it will be different from the correct answer. So let me write here another section for the answers. Okay, so for A, we use 0.3 0.3 seconds in here and solve it. So please put your calculators in radians, or if not, if you want to use degrees, we'll just follow this one. So we write our S would be equal to 5 over pi sine of 2 pi times 0.3. Since this is in radians, and if you want to use degrees, we need to multiply it by 180 over pi, or that's approximately 57.3 degrees, which is equivalent to a radian. Okay, so let me put this in brackets and plus our initial position, which is 5 centimeters. Okay, you only do this if you kept your calculator in degrees. If you put it in radians, no need to multiply by 180 over pi. Okay, so plugging in in our calculators, that's, we cancel pi here, so that would be 2 times 0.3 times 180 degrees. That's around 2 times 0.3 times 180. That's 108. Okay, so sine of 108 degrees, or if you like, that would be sine of 2 pi times 0.3 in radians. Okay, so at this point, I hope you know how to manipulate your calculators. So we will just be doing this computation for the first one, and I will just be plugging in or writing down the answers for the next for B, C, and D. So I just want to emphasize here the process, how you do it, because we initially in the problem, we are informed that the angle 2 pi t would be in radians. So depending on the mode of your calculator, please do the proper adjustments. So for this one, we got the value 6.0 approximately 6.51 centimeters. So doing all this again for 1.4 seconds for B, C, and D, we got at 1.4 seconds, the position is 5.94. So if you notice, it somehow went back, right? So it's not really going from 0 um up to the measurement is increasing. It's not actually because of our function here, this function. Okay, so it depends on the cosine of 2 pi multiplied by the time that is in radians. So for C, that's 2.9. I think we got a negative value for the sine. That's why the position is 4.06 approximately centimeters. So just do this again on your calculators, but using the time here, 2.9. We get approximately 4.6. So again, if you notice, our initial position is 5 centimeters, but now we went back. We are 4.06 centimeters after 2.9 seconds. So at 3.6, it's approximately, they're not really, these are just approximate values. So you can see it's also 4.06 approximately. This is rounded off. So they are not really in the same position at the same times at 2.9 and 3.6. Okay, so this is just to analyze the motion. We really don't need to get a headache from it, but what we need is to know how to use our knowledge of computing the partial solution of the DE to this application, rectilinear motion. Okay, so now we have solved the what is required in the problem. Okay, now let's take another problem regarding rectilinear motion, but this time here this is horizontal motion. Now let's go to a vertical one. Alright, so here a stone, so our particle now is a stone and it is thrown vertically upward. Okay, so let's assume it's you throw it straight upward. Okay, so vertically upward, no angle. Okay, so vertical only from the ground, where the initial velocity is 128 feet per second. So now we are dealing with feet or English system. Okay, feet per second. So consider that the only force acting is attributed to acceleration due to gravity. So what is acceleration due to gravity? So we all know it's 9.8 meters per second squared, but we are dealing with feet here. So we need the counterpart in the English system, which is 32 feet per second, and it is always directed towards the center of the earth. So it depends on which axis are we going to assign as the positive one. But in if we are going to use the Cartesian coordinate plane system, going down would be negative. Okay, anyway, let's just continue reading the problem. So this is what the problem wants us to find. A, how high will the stone go? So if we throw it with an initial velocity 128 feet per second, and we are the stone will be acted upon only by the force of gravity. Okay, so we neglect if there is a wind or whatever other forces there is. We just assume that the only force that will act would be acceleration due to gravity. So it means since it's opposite the direction, it will slow it down. So until the velocity is zero, what is the distance traveled by the stone? How high the stone will go? Okay, so I'm trying to discuss here now how we will approach the problem. Okay, it's better to draw it later to visualize it. So, and B, that's not the only that's not the only one we will be solving. B, how long it will take for the stone to strike the ground. So of course, if you throw it from the ground, it reaches a velocity. Since it is opposed by gravity, the velocity will become zero, and it will eventually fall down with an acceleration which is equal to the acceleration due to gravity. So how long it will take for the stone to strike the ground as it falls. And C, when the stone hits the ground, what is the speed or what is the velocity at that? So let's use the term here, instantaneous velocity. Okay, so what I want you to picture is the motion is the motion is ongoing, and we have the ability to take screenshots. Okay, an instant of wherever we like. It's like pausing the motion. Okay, so from the initial one, okay, I think it would be better to draw it. Okay, so this is what is asked in the problem. Okay, so let's go to our whiteboard and try to make sense of the problem. Okay, so firstly, we write our given. So what do we have? So number 1, so in our given, let's also draw our motion. Okay, let's say this is the ground. Okay, so the stone will be coming from here. Again, it is better for us to imagine the motion as the whole motion, and we can take screenshots or we can pause it. Okay, so this is the stone in the initial condition where it is said that the initial velocity v sub o would be 128 feet per second. This is at initial time, which is 0. Okay, so at 0, it's on the ground. This is the ground. So this ground. This is our stone initially 128 feet per second. So now let's try to simulate where the stone is going. So please pardon the drawing. It won't really be straight. Okay, so the stone is opposed by the force of gravity, which is, let's write it as G. Our G, since we are operating in feet, let's say our G is in approximately 32 feet per second squared. G is acceleration, so it will be having units of feet per second squared, and it's going downward, so we write it as a negative. Okay, so here our analogy would be that the going up the vertical axis, and that would be the positive axis. Okay, positive motion. All right, so this is not really the assumption in the problem, but I would just want to write the stone. Okay, the stone is here, but practically, or according to our assumptions, it is a straight motion, so it will go up this way, and it will also fall this way. Okay, but let's just write it like this for to visualize it easier. All right, so this is our initial conditions. Let me label that as our first screenshot. Okay, so for this, the instantaneous velocity at this instant, okay, is 128 feet per second, and the time is 0. Okay, and then we throw the stone, and I want to write the second. We pause again the video and or the motion, and I want to label it at this one. This is where we pause it, and assuming this is the highest point. Okay, so this one is unknown, so let's label this one as v1. Okay, or if you want, let's use vh to say it is the velocity at the highest point where it stops, so that would be 0, right? So if we throw it and it is constantly acted upon by the force of gravity negative 32 feet per second squared, it will eventually stop. Okay, the particle or the stone will stop. So at that instant, we pause it, we take the measurements, and we know that at that instant, the velocity at the highest point would be 0 feet per second. Okay, so if you didn't understand that, just try to rewind it for the explanation. Okay, but we also don't know what is the time, right? We don't know. We right now we still don't know at what time our stone will reach the highest point. Okay, so that is actually true. We have no way to know right now, but using our analogy, I promise you, we can solve all these unknowns. Okay, so now the next screenshot I want to take, or the next pause I want to do, would be when the stone hits the ground. Again, this is just to visualize it properly. Okay, so the ideal one is that this stone will go up, stop there, and then will fall and go at the same place. Okay, so please don't be confused. We don't have a function for along the horizontal axis. That's why. Okay, so now let's take the screenshot in here. So when at the instant the stone touches the ground, we want to know what is the velocity there. So I don't know what you want to call it, but I want to call it final velocity. Okay, so vf, that is, do we know it? No, we don't. We need to solve for it. Okay, so this is one of our required. This is unknown. And what is the time? The final time, let's just call it final time. So of course, if it hits the ground, it will have some further movements, but we are not concerned with that, with this problem, because we already defined earlier our requirements. All right. Okay, so this is how I will tackle this problem. All right, so we have the initial instant, or the screenshot for the initial conditions. We have the screenshot at the highest point. Okay, we know the velocity there would be 0, and the time there would be, we will solve for that. And the third instant, or the third screenshot, would be when the rock hits the ground. Okay, so we pretty much have already defined our we already defined our givens. So what, let's write down again our required in terms of our variables here. So I think I need to go back to the slides. We need to find A, how high the stone will go. How long it will take for the stone to strike the ground. And C, the speed with which the stone strike the ground. Okay, so C is speed, B is time, and A is distance. Okay, so A, we need, let me introduce another one here. So in this instant, what is the distance? So S sub H, at what is the highest point? Okay, so we're looking for, in A, we're looking for S sub H, the distance on the highest point. We're looking also for B, the time at the highest point. And C, we're looking for the speed. Okay, so we are looking for the final velocity. So if you can see here, at this point, we are looking for two unknowns. We have the distance, S sub H, the highest point. We have the time to reach that distance of 0, velocity, highest point, and C, when it falls down. Okay, so let's proceed to our solution. Again, I think you know that as we are given initial conditions, we are looking for the particular solution of the differential equation. And what is that differential equation? We have here G. This is defined as acceleration due to gravity. So we know that acceleration would be equal to change in velocity over change in time, or dv over dt. And our acceleration is given as this. So since we chose the vertical upward direction as the positive one, we will be using the acceleration due to gravity with a negative sign. Okay, so since acceleration is equal to dv over dt, we can simply write that again as dv over dt equals negative 32, let's write the unit, okay, feet per second squared. Okay, so this is our differential equation. So solving for that, for the velocity, we have dv equals negative 32 feet per second. Okay, I will not write down the unit for this, for to easier to see it easier. All right, so now we want to find the equation for the velocity. Okay, so let's integrate this one, antiderivative. So v would just be equal to negative 32 t plus the constant of integration. Okay, constant integration c. Let's call it c1, since you know that we will be needing to integrate that once more, and we will have a second arbitrary constant. So now this is our equation for, this is a general solution for the velocity. And how can we get the particular solution to this? By plugging in the values, the initial conditions. Okay, so here, this is our initial conditions. So V sub O would be equal to negative 32 T sub O plus C1. Solving for C1, here C1 would just be equal to, since T sub O is 0, this whole expression would be 0. So C1 would just be equal to the initial velocity, which is 128 feet per second. So as I've reminded you earlier, most of the time the arbitrary constant is just the initial condition. So writing again this equation for our velocity, so our velocity at any point in this motion would just be equal to negative 32 t plus the initial condition 128 feet per second. Okay, so now this is our particular solution. So how will this particular solution help us in solving our required, you may ask? So for E, we are looking for the position. Are you seeing any position here? Right now, no, I believe. B, we are looking for the time. So can we solve for the time now? So I guess we can. Okay, let's do that for later. Let's find the highest point first. Okay, so how do we do that? We know that the velocity is just equal to ds over dt, and velocity is equal to negative 32 t plus 128. So separating the dE, we have ds is equal to negative 32 t plus 128 dt. So to find the equation for the position, we should take the antiderivatives of this. So the antiderivative of ds would just be equal to s. That would be equal to, so I hope you don't mind if I do some shortcuts here. I hope you can follow. You just pause the video and try to solve it on your own, but this would just be simple power formula. So this would be negative 32, that would be t squared over 2. So rather this would be negative 16 t squared plus 128 t plus our arbitrary constant C2. Okay, so now again we have another complete solution for the dE, this dE, solving for the position. Okay, so now that we have this these equations, how will this equation help us to find our records, which is the highest position, the time at the highest position, and the velocity at the final position or in the ground. But before we proceed, let's take um, the value of this second arbitrary constant, so that we will have two particular solutions. So in order to find the value of the second arbitrary constant, this one c sub 2, we need to plug in again our initial conditions. Alright, so let me just write here that at this instant where we thrown the stone and our reference point is the ground, so our S sub O, or initial position, is also at 0 feet. Okay, so if we plug in here 0 equals the time is also 0, so all of this is 0, we can conclude that our arbitrary constant number 2c2 would just be equal to 0, and our equation will be reduced to just this. Okay, so let me use another blank whiteboard. Okay, so let me write the first particular solution in terms of the velocity that we have. That's v negative 32t plus 128 negative 32 of t plus 128. This is a particular solution. And S, now that we know that the arbitrary constant C2 is just equal to 0, so now we know that this is just, we can write it as this. Okay, so for that, first please let me correct something. So here at B, we're going to solve for this time. We need to solve for the time where the highest point is reached, but according to the problem, it's not really what we are looking for. So B is how long it will take for the stone to strike the ground. Alright, so let me just correct that. It means that we are not looking for the time at the highest point, we are actually looking for the time it hits the ground. Okay, but then again, we will also solve for that time since we need to know that distance. Okay, so let me go back there. Okay, so let me repeat that. We are looking for that. For B, we are looking for the time that the stone hits the ground. Okay, but we are still gonna solve for the time when the stone reached the highest point. It's just not in the required, but it is required in the problem, so that we can solve for B and C. Okay, so now let's go here. We have these two equations. So the first unknown for us would be A. What is the distance at the highest point? And we can only solve that by knowing what is the time, this one, at the highest point. So we can actually use this equation to solve for the time. How? We know that the velocity at the highest point would just be 0 feet per second. Alright, so if we substitute 0 here, we velocity at the highest point. Okay, let me rewrite the equation. So the velocity at the highest point, this one, would be equal to negative 32 t at the highest point as well, plus 128. Okay, so since this is 0, this is negative 32t plus 128. We can solve for th, right? So we transpose this. We have 32t at the highest point would be equal to 128, and we divide both sides by 32. This would be 32. So the time for the stone to reach the highest point would just be equal to, this is cancelled, and this would be 128 divided by 32 is 4. Okay, so the time to reach the highest point would be 4 seconds. Okay, so I hope you can follow the analogy. We want to know the time at the highest point is not really asked in the problem, but we need this in order to find the distance. So going from this equation to this one, this is the equation for the distance as a function of the time. So we want to know what is the distance s at the time the stone is in the highest point, which is we solved as 4 seconds. So going to this equation now, we can solve for s at the highest point. That would just be equal to 16 time at the highest point squared plus 128 multiplied by time at the highest point. So let's plug in 4 seconds in here. So the distance in the highest point the stone will reach would be negative 16 multiplied by 4 squared plus 128 times 4. Okay, so if you will plug that in your calculators, this would be negative 16 times 16. Remember, that is a negative value. You have 128. That's 256 times 2. 256 times 2, and this would be negative 16 times 16. So the answer, okay, that would be negative 256 plus 512, which gives us 256. This is a distance, so this should be in feet. So units check, this would be okay, this is distance, so let's just put feet here. So this is 256 feet. Since this is positive, so we defined earlier that the direction upward would be the positive distance. It means this is 256 in the air. Okay, so let me just give you an idea about that. So this height would be 256 feet. Okay, where the stone will reach a velocity of 0. So we started with 128 feet, and since it's constantly acted upon by negative 32 feet per second, so the velocity will be constantly decreased until it reaches 0 at this point, and this point is 256 feet, and earlier we solved that it takes 4 seconds to reach that. Okay, so I hope you are following and you are appreciating the analogy and the application of our DE. Okay, so we have the H at 4 seconds, and the highest point would be 256 feet. So now we have an answer for our A. Okay, so S of H, the highest point would be 256 feet. So now let's go to B. What is the time that the stone will hit the ground? Again, we will rely on our two particular solutions here to solve for that. Okay, so let me write down here that this is our solution for A. Okay, and we've solved this one. Now let me have another one, and this is for B. So going back to those equations, we still have these two equations. So now how will we solve for the time at this point? This one here. We don't know the final velocity yet, and we don't know the final time yet. So we will still be utilizing the particular solutions that we encountered. So since we don't know the velocity, it looks like we cannot use this equation, right? We will just have two unknowns. So let's take a look at this one. Okay, so at that position in the ground, what is S? So the position there would be 0. Okay, let me write this equation on the other page. So S is equal to negative 16t squared plus 128t. So in terms of the final position, let's say SF, the final position, we have negative 16tf, the final time, plus 128tf as well. So we know that at that point here, at this point, let me write here that SF, we went back to our initial position, which is 0 feet. Okay, so let's substitute 0 in here. So we have 0 is equal to negative 16 tf squared plus 128. So since t, the only variable left is t, we can solve this equation. So I will transpose this to the left side. That would be 16 tf squared is equal to 128 tf. So we can find the value of tf by dividing both sides by 16 tf. So for this one, the 16 will be cancelled, 1t will be cancelled, and what is left is tf. That will just be equal to, let's divide this one with 16 tf as well. Okay, so this is cancelled. 128 divided by 16, that would be 32, 64, 120. Okay, that would be 8, right? Okay, that would be 8 seconds. So now we know that the whole motion from the ground to the maximum height that we solved earlier, which is 256 feet, and then going back to the ground, that round trip will take 8 seconds. Now the last thing asked in the problem is, what then is the velocity, the final velocity? So we have the equation negative 32t plus 128, and we have the value for tf. So let's write it down. So v F, the final velocity, will just be equal to negative 32 multiplied by the final time plus the initial condition, which is 128 feet per second. Okay, remember that the unit here is feet per second, so the final unit would also be in feet per second. So let's plug in our values. So V sub F would just be equal to negative 32 multiplied by 8 plus 128. So that's negative 32 by 8. That's negative 256 plus 128. So the final velocity is negative 128 feet per second. Oh, sorry. That's only feet per second, not per second squared. So you may ask, why is the velocity having a negative value? So this is the value of the velocity that we have. Okay, so the negative symbol here is just denoting the direction of the object. So initially we decided that the positive direction would be the positive y-axis or upward. So this time our stone or our particle is going downward. That's why we got a negative here. But in if we will shift the axis, it will give us the absolute value of this, of the velocity, would be 128 feet per second. Okay, so this negative sign is just denoting the direction. So if it's asking you about the magnitude, we know that velocity is a vector. Okay, so this negative sign is just denoting its direction. So this is our answer for the final velocity. We can keep it as negative 128 feet per second. Or if the problem is just asking about the magnitude, we can write 128 feet per second. But just in your succeeding problem solvings, just keep the sign, since it's a vector and it's just denoting the direction. Okay, so let us now compile our answers. Okay, so for A, we are asked what is the highest point that our particle will reach, and we solve that as 256 feet. For B, it is asking how long the trip will take, or at what time the stone will hit the ground given the conditions, and we solved it as 8 seconds. And for C, we solved it as the final velocity is equal to, I will keep the negative sign, negative 128 feet per second, or 128 feet per second, and you denote the direction as downwards. Okay, so that's the same thing, saying it's negative 128 feet per second, or saying that's it's a downward motion with 128 feet per second magnitude for the velocity is the same. Okay, Okay, so that ends our lesson. So as if you want to review, our source is still this book, Calculus 7, and you can find this lesson in page 336 to 343 if you have anything you want to clarify, or you can send me an email if you have questions, or just fill up the questionnaire, our Excel sheet, or if you have any questions, don't hesitate to contact me, and I will answer you to the best of my abilities and as soon as I can. Okay, so for this lesson, thank you for watching, and good luck on the problem sets.